Yeah. Okay, next topic, precise temperature control, which improve efficiency, precision, and user experience in the fabrication. Accurate temperature control is highly essential in the production of high-quality dental prostheses. Dental ceramic furnaces use a high temperature to fire ceramic materials, so temperature control is a highly necessary need to avoid damage to the ceramic material. So why it's necessary? First, it prevents any cracks, bubbles, or distortion. Also, the final product would be strong and durable with proper adhesion to the underlying glue structure. So, a well-designed dental ceramic furnace should have a programmable controller that enables precise temperature control. And this difference is one of the differences between the conventional furnaces and the modern furnaces. And this difference, I will talk about it in the next topic. Before talk about the modern furnaces, I'll talk about the conventional furnaces. The conventional furnaces don't have temperature control systems and use external devices to measure the temperature. And these devices can come in two types. The first type, which is the thermocouple. It's like the mercury thermometer that we know. The thermocouple placed in the upper section of the firing chamber at the close distance from the ceramic object and then measure the temperature of the ceramic object. The second type, which is the infrared camera, same principle, which is directly placing it on the object in the firing chamber and measure the temperature. Now, regarding the modern furnaces, they include something called PID program, which is stand for proportional, integral, and derivative. This program has three modes of action. The first action or function called the proportional function, by its name, proportional, which means adjusting the temperature according to the feedback, which means if the temperature raised inside the firing chamber, this program will decrease the temperature and vice versa. And this is the main function. The integral function remove minor temperature instabilities while firing, which means a minor fluctuation along the firing process. And the third function is the derivative function, which prevents the initial power overshooting. Now, this PID program doesn't exist in the conventional furnaces. Now, why calibration is important, which is an advantage used or exists in the modern furnaces? Because improper temperature control can cause soiling and deposits in the furnace, which lead to changes over time. Also, the technical components, such as the heating wire, the stone insulation inserts, and the heating muffle, can also be affected by wear. So calibration ensures that temperature control is correct again. If you do not calibrate, this will lead to a faulty temperature in the furnace, which could negatively affect your restoration. Programmable firing cycles tailored to specific ceramic materials and restoration types. Here, I'm going to talk about the other advantages of the modern or the other features of the modern dental furnaces. The first one, the memory system that can remember even up to 200 different programs, which can be performed accurately by the user. The second feature, the multi-stage programs that used for firing or sintering for ceramic materials, where it's necessary to heat and hold at one temperature and then heat or cool at to another program temperature. And this second feature because of this criteria, there was an ability to create several programs that have different temperatures, different rates, and holding times. And this is necessary to specify, which give a specific programs for each restoration. You know, each restoration, each ceramic material has its need. So it's a good idea to have a specific program for each material or restoration. Third feature, which is, of course, the digital display, show you the current program information and the status of the process progress. And the fourth one is the automatic prevention of condensation in the firing chamber. As you know, each restorative material has its own firing program. An example of these modern programs were mentioned by Esai and his colleagues in 2015 for zirconia restorations brand Incoris Zirconia and Incoris Tetragonal Zirconia, which included 3 programs for each material. I talked about this example for 2 reasons. I want to show you how single restoration can be fired by different programs, which is a criteria for of the modern furnaces. And also because this brand or this system was involved in a comparative study about the effect of firing program, effects of different temperature, effect of different duration, their effects on the mechanical properties, which is the next topic. So for this brand, for example, there was 3 programs. First program, the slow sintering program, which is the regular one. Sintering was done at 1510 Celsius, and the total needed time was 8 hours. The second program, which is the faster sintering program, used a higher temperature than the previous one, and the total time was 2 hours. And the third one, which is the super speed program, used even a higher temperature than the previous 2, and the total time was only 10 minutes. Regarding the next topic, which is rapid heating technology, without compromising the quality of ceramic restorations, Erso and his colleagues also compared the effect of different sintering temperatures and times on the flexural strength of zirconium. And the results of this study showed that experimented higher temperature, the high sintering temperature and the short sintering time combination, which is program 3, increases the flexural strength of zirconium, which means that rapid heating for the system used enhance the mechanical quality. Now, regarding the gradual cooling to minimize the risk of ceramic fracture, you know, residual stresses in porcelain cause clinical failure, such as fracture or debonding of the veneering porcelain. So, Ibadian and his colleagues in 2018 suggested that porcelain cooling protocol may affect the amount of residual stresses within porcelain and also porcelain zirconia bond strength. Also, they assess the effect of cooling protocol on the fracture load of porcelain veneer zirconia restorations and found that slow cooling protocol should be preferably applied for zirconia restoration. And the reason was attributed to the low conductivity nature of the porcelain. When you have rapid cooling for all ceramic, the superficial layer will lose its temperature or will have a sudden decrease in the temperature, while the inner layer, the underlying layer, is still warm, and this will create tensile stresses. And this tensile stresses may lead to fracture or debonding for the veneering porcelain. Thank you.
العافية مجد.
الله يعافيك.
يعطيك العافية مجد.
الله
Thank
يعافيك.
you very much, Dr. Majd, for your presentation. I appreciate it very much. And I would like to open the floor for questions, if you have any, for your colleague. Any questions?
لا دكتور، ما يعني أنا ما عندي specific questions أو question مكان معين يعني. أتوقع إنه
Okay.
كانت الفكرة comprehend يعني أمورها تمام.
Okay.
Any
Perfect.
suggestions for the design?
يس دكتورة، كان كل شيء واضح. بس دكتورة أنا
Okay.
بس عندي يعني لما تكلمت عن الفور واي زيركونيا اللي هي الترانسلوسنت،
5
انه بيكون different compositions، انه بتكون 4y بعدين 5y عشان يعطوا البوليكروماتيك effect.
Yeah.
في studies انا قرأتها انه بينعمل two types. one type اللي هو بيكون different compositions، وفي type ثاني بيكون single
Yeah, I
composition
talked about that.
4y.
Yeah. I mentioned that it can come in uniform composition or different composition, but the different composition will give you a better results because you will end up with a gradient not only in the natural consistency of the two structure, but also gradient in the mechanical properties. That's why it's preferred to have a mix of different materials. Each material give you an advantage.
Okay. Yes. It's actually the translucency, not the pigmentation. The pigmentations or multi-layering or colored types of ceramics, they add some stains to it. Okay, so the effect of the yttria is actually first on the translucency. This was the derivative for the production of this material that
Doctor,
produce
they mentioned,
translucent material.
yeah.
Then they found when they done it that they have reduced forces, strength forces. Okay, so that's the idea about it. Okay.
Doctor, they mentioned that the yttria concentration control the or the amount of yttria control the translucency, the amount of yttria control the color, pigmentation control the chroma. So each
Okay.
component control something.
Okay.
Yeah, they talked about it.
Oh. If you go back in your slides, maybe it's something. If we go back to the beginning, please. Okay. If you go down the slide. Okay. Terms of same-day crown and bridge fabrication. Did you find anything about that?
I talked about it, Doctor. I talked about the workflow. I talked about the currently available chairside material. I talked about the comparative studies between them and the conventional methods.
Okay.
So it's all about the,
yes.
yeah.
Are these this CAM technology, is it in clinic or with a lab work?
No, chairside.
Chairside. So
Yeah.
what are extra steps that you're going to have included in the procedure after the milling?
Actually, I think it's less steps, and chairside less steps, not more steps.
More, yes, exactly. So just I need you to compare between the material used for the milling that goes into the mouth in the same clinic, meaning that does it need further centering or not? Does it need further glazing or not? So it will depend on the block or the material that you're provided with. Are these ingots or discs? How are they going to produce? What are the percentages in terms of if there's expansion or no expansion, and how did they overcome it if they were going to use pre-centered discs or ingots? Okay.
Yes,
Advantages
I think it
and
depends.
disadvantages.
Yeah, I think it depends on the material.
I definitely depends on the material, but the idea is it depends on what further steps or procedures you need to apply to the material. So if it needs a centering, that means you have to compensate by volume shrinkage and expansion. Okay, the dimensions you use are usually expanded. But the problem is that they are easy to mill. The burrs don't abrade quickly. But at the same time, we are going to have a centering time. We have to do centering and then the glaze. While if I'm milling into a block that is already centered, okay, that will usually these are softer blocks and they come as ingots and they are less strong material. So just try to do that comparison, please. Just a comparison. It's like 1 or 2 slides
So
on shelf
um,
side CAD/CAM.
okay, but if this depends on the material,
I know the
I
material,
have
but
to
if,
go through each material.
no, if you can bring one
have to go
example,
each-
one example for each. I'm talking about pre-centered
Okay,
versus centered. One for ceramic, one for composite, and compare between them. And lithium disilicate. These are the big names, let's say, or the big applications. Also feldspathic. The idea is when you have pre-centered material, that means it's more difficult, more time consuming to mill. You have saved some time in
Yeah.
the furnace, but you have not saved it clinical or milling wise. Then you have the abrasion of your burrs. And finally, there's
Yeah.
always a glazing step. So you also still need a furnace besides you in the clinic to do the glaze, the final glaze after the adjustments. Okay, just a quick slide. It's just 1 or 2 slides, just looking at the time spent milling, time spent clinical adjustments, and time for glazing, and the need for centering, further centering. Okay.
Okay.
Okay. You talked about
Doctor, what's the third? Milling adjustment, and what's the third?
milling time, centering time,
Yeah, adjustment time, centering time.
clinical adjustments.
Yeah.
Okay, and the need for the effect on the burrs,
Effect
on the
this.
milling, the burrs used in the milling machine. Okay, okay. You
Okay.
talked about multi-layer ceramics. Okay.
Mhm.
I would prefer if at least you could show some products that have multi-layers, because the way they are added into multi-layering, these are different for different companies. For example, some companies have only 2 layers. One is lighter than the other. They might have 3 layers. Some companies have even 4 layers. And within these layers, some companies have all of the layers within, for example, 5 yttrium. Others have 3 yttria,
Okay.
and on the enamel surface, they have that as 5 yttria. So there are some variations in terms of the multi-layering between companies. We need just some examples of how do materials shift
You need
within the
brand name
multi-layering.
about, yeah.
Any brand.
I have an
The idea
article.
is,
Yes.
yes.
Mm.
Is there an article about this?
I think yes. Article conducted by Ben. He classified the zirconia into 12 types. They consider all the modern and recent developed zirconia, including the multi-layer, the uniform composition, the amount of yttria, percentage, everything. I will check if there is a brand name, some brand names.
The paper will be satisfactory. If that paper is present, please add it to the slides. Like 2 or 3
okay.
slides where you show the differences between different disc shapes and how do they come in terms of color. Okay? Or ingots. It could be a disc or an ingot with multiple colors. Okay.
Okay.
When you were talking about the forces and the applications of these material, if you go back to the slide where these are used for inlays, onlays, or the one with that had a schedule. Okay.
Okay.
Yes, this one, please. This one, you got this reference, but still we have something, we have another table that it goes for the indications in terms of the megapascal of the material, that how much does it hold in megapascal. Okay.
Yeah, fracture strength, fracture toughness, fracture
It's
strength.
present in the ISO. It's present in the ISO for ceramics, and it's also present in some papers where, even in your textbooks, what are the megapascals that can be tolerated? Why? Because sometimes you can see these indications, but what if the same material have produced better strength? For example, if we're talking about zirconia, for example, you say crown bridge, but when you go to the new types of zirconia, we'll find different strengths. So some of the most advanced ones, or the hybrids, or the whatever the types are, they have strength megapascals lower than the recommendation. So it's good for you to add the megapascals and try to put the new types of zirconia in that scale, the 4th generation of zirconias. So one slide for each indication and terms of megapascals that are recommended for this application. One slide.
Okay.
Okay. Then the slide after that is what are the megapascals of the new types of ceramics.
Okay.
And from there, we could join or put them in two tables just side by side, and let us see how strong are these new material. So are we able to use them as inlays, overlay, or crown, or bridge, or posterior bridge, or so on? Okay.
Doctor, you also asked me to specify which type of zirconia. They didn't specify in the article which type of
No
zirconia.
need. At least one or
Okay.
two. You have a big brand
No,
types
I
for
mean
generation.
this table.
Yeah, but at least one product. You can bring one or two products.
Okay.
Okay. Milling machines. You have talked about the design, but you haven't talked about the milling machines themselves.
Okay.
Okay, the milling machines have different types. I want one or two slides just showing the components of a milling machine. How
The dry and wet milling. Okay.
yes, and
5
also
axis.
pre-centered or centered material, and the number of axes.
Number of axes.
Number of axes,
Yes.
2 or 3 axes. Okay. The number of bears, 1, 2, or 3, or up to 5. We have something with up to 5. So 1 or 2 slides with the indication. For example, if I have some undercuts that I need to add, I need like 4 and 5. The more complicated the morphology of the prosthesis I'm doing, I need more bears to go into the small details. Okay. So if you can show us these types and their indications, when is one bear required, 2 bears, 3 bears, and so on. Okay. And the same applies to the bears themselves. What are the types of bears used in these milling machines? Okay. Just 1 or 2 slides for the milling itself, milling machine, and its classification in terms of the axis and the number of bears. Secondly, the bears themselves. What are their classification? What types of bears are used, and for each material, for example. Okay.
Yes.
So, furnaces show a control panel. It's beautiful for you to also add 1 or 2 images on one of these programmable furnaces. What does their screen show you? What can you program? Because there's some lack in the number of images. Okay.
Okay. Because the article lack these images.
Yes, I know. Articles do, but you can find some. There are some product, let's say, some commercial websites. They give you like comparisons between those furnaces and what can you control and how to use them. So if you don't find them in papers, you can find them in product comparisons pages.
Okay.
Okay, just 1 or 2 slides, just showing you what can you modify and where can you see it on the screen.
Yeah.
Okay. Also, when you talked about the furnaces once more, you talked about they have different cycle phases. And you have you have something called heating time. Okay, and that's usually displayed in. So it's not only if I'm looking here, for example, the slope centric program. Regular, you're talking about the temperature. Okay, and the dwell time, but you haven't talked about the heating time and the cooling time. Okay, because these are also
again,
added to the cycle.
Yeah, it wasn't mentioned again.
It's
more dependent. Yeah, Doctor, I was more dependent on articles rather than manufacturer catalogs or
we don't need the exact detail for a specific product. It's just showing these variations because we have different times for the cycles. We have heating time, which is how many centigrades does it increase per minute. Okay. Sometimes we have what we call preheated cycle, where we preheat and then we enter with our material. You have the holding or dwell time, the holding time where the temperature stays consistent, or sometimes the dwell time is not consistent. Maybe the dwell time is staged, meaning in the first, like say 20 minutes, it's so and so degree, the second stage. It's just these small diagrams that show you different cycles present in these furnaces. Okay.
Yeah.
Finally, you talked about the furnaces and their effect on strength. One of the papers talked about the effect of strength.
Yeah.
The effect of strength really depends on the material itself, because the material, I mean, the same material, but still we have different companies, for example. It also depends on what are the phases present in the final product. You know that zirconia is tetragonal, monoclinic, or
Monoclinic,
cubic.
tetragonal, or yes, cubic.
Yes, cubic. So what happens to these powder particles when you heat them? And this is what actually affects the strength of the material. Okay, so the quality of the furnace and how these are fired, these materials are fired in the furnace will give us different strength. So it depends on these values. So if you show one, there are many papers that show this, but I want to show you, to show us how were the shapes of different final product, the grain size, and how they were seen in the papers. Okay, you will find them easily in papers where they compare the different sintering cycles with the strength. If they have done a scanning electron microscope after, you will see those images. This is important for us to really capture the idea of how does the cycle of the sintering affect the flexural strength. Okay, one slide or two slides.
Effect of phases or grain size on the mechanical strength.
You will see that there are different temperatures, and they will show you the particle sizes in images, and they will tell you this phase is responsible for this strength. So try to find one or two slides. Yes, because it's important. The studies you have brought about the effect of cycling the furnace or the furnace procedure, or let's say furnace cycle in the sintering procedure, I found that the samples were all about veneered zirconia and the cracks in veneered zirconia. We need at least one study on the effect of monolithic zirconia.
The idea was to see the effect of the gradual cooling or rapid cooling, which one caused the fracture or debonding with the veneering porcelain.
Okay, these are veneered zirconia, Mr. Jesus. I'm fine with this. I'm fine. But now we have a lot of monolithic zirconia.
I agree. But the idea of this study was to explore why rapid cooling caused the fracture of the veneering porcelain.
Once more.
That's it.
Fine. I'm fine with this paper. I'm not. Don't have a problem. But I need to know what are the effects of different heating cycles on monolithic zirconia, not veneered zirconia.
Cycles and
monolithic.
Cooling?
Monolithic
cycles.
Zirconia.
Cycles and cooling on monolithic.
Monolithic effect on monolithic material. Do they produce cracks? Do they produce any change in particle size, which are the grains or the grain morphology of the crystals of the zirconia and so on, and the size of the grains of it?
The effect of the cycles, not the cooling.
It could be the cooling, it could be the cycles. I don't know what are present, but the idea is talking about thermal stress and monolithic zirconia, not veneered zirconia. Okay. One or two papers, or you might find a review first. If you find a review, it will sum up the material.
Yes,
always when we are looking at any study, it's better for you to produce to bring a review rather than a single study. Okay.
Yeah.
Because in a single study, for example, they have seen there is no difference. Maybe another study found some differences in terms of grain size and the crystal shape. Okay, the resultant crystal shape. So these are important. If you can add them, please, to this presentation.
Okay.
Okay. Thank you very
Okay.
much.
دكتورة
Any other question?
yeah these two topics again, I didn't find anything regarding the high energy efficiency.
Okay, these are talking about different ways of heating a furnace and how many watts and what is the energy consumed. Okay, you haven't found them in papers, yes?
Yes, I didn't find any. I also didn't fully understand the idea, conflicting high energy and at the same time minimizing the energy consumption.
Okay, what else did you find?
It's conflicting. ايش دكتورة؟
Any other thing that you didn't find?
Yeah. Multi-stage firing, for example.
Okay, this is what we said about the holding time. Multi-stage firing is not actually going up and then dwelling and coming down. It is graded.
No, I understand this idea, but I didn't find anything
didn't find any
remarkable about it.
Okay, and
neither paper nor
as well. There are multiple firings as well. Other than multi-stage, also multi-firing effects on the restorations. So all of these come in different papers and different studies.
Okay. So in this topic, you need an example, for example, brand name for firing furnaces or what?
What does it mean?
Firing?
What does multi-stage firing mean? And how you apply it? One or two
multi-stage
slides.
It means, multi-stage means the temperature goes up and goes down and goes up again.
No, doesn't go down. It's the key dwelling time is multiple temperatures, not one stable temperature all through. Okay.
Okay.
Cooling, gradual cooling. These are also all of these. Okay, are related to the furnaces and how they are programmed. Just give like an indication. Why is this used? Why is this used? What benefit do I get from this? What do benefit I get from this? Okay. What do these add? These are the changes in the furnaces themselves. Okay. So all of these are included. These should be like subheadings of this.
Okay.
Any other question?
No.
Okay. In our next presentation, we're going to take a break for 10 minutes. And then in our next presentation, we're going to talk about how to use the medical terminology and the keywords. Do you remember we talked about MESH when we talked about the papers and how to take them or use them? We're going to go through an exercise. We're going to know how to use these terminologies and keywords in scientific terms and how do we know their actual definitions, okay? So 10 minutes and we'll be back. Thank you very much.